All right, so in this presentation, I'm going to be describing to you how to determine the electron configuration of atoms, and we're going to be talking about what is called the quantum mechanical model. So let's discuss what is the quantum mechanical model. Before you do this, please make sure that you've watched the video on the photoelectric effect, because we need to understand how it is that light is a wave that acts like a particle, because this idea is what led to the quantum mechanical model of the atom. So a gentleman by the name of Louis de Broglie actually came up with this beginning idea of the quantum theory by thinking about the idea of an electron, that it doesn't move in a straight line. So if light is a wave that acts like a particle, that means that particles can move like a wave, meaning in a transverse wave pattern in a three-dimensional space. So in 1923, he reasoned this idea and postulated that a particle, okay, with a mass and velocity would have a particular wavelength. And he created a calculation for it, which right there we have wavelength is equal to a constant, h, which is Planck's constant, divided by the mass and the velocity. Velocity just a fancy word for speed. Okay? So in his hypothesis, he actually was able to prove it by experimentation. And in his experiments, he found that electrons could be diffracted, meaning that they could be bent around an edge of an object through a small opening, and that they would also experience what is called interference. This therefore proved that electrons were moving in the pattern of a wave, meaning they're not going in a straight idea or a straight line. Okay? They're going in a wave-like pattern in a direction. So if matter actually has wave properties, why aren't we able to see them? Why is it that when I throw, for example, a baseball, I'm unable to actually see it move in a wave-like pattern? Well, the reason is that the wavelength is so tiny. So if we use a baseball, which has an average mass of about 0.145 kilograms, and let's say we throw it at 60 miles per hour. No, you're not going to the major leagues with that. It actually has a wavelength of about 1.7 times 10 to the negative 34th meters. That wavelength is way too small. However, what if we're dealing with an electron? What if we were to change the mass to be something like 9.11 times 10 to the negative 31st kilograms? That would make it, ladies and gentlemen, to be a much larger wavelength, one that could actually be measured. So a gentleman by the name of Werner Heisenberg in 1927 developed an actual principle. And what he stated is that it was impossible to know the exact velocity, meaning the direction and speed, and the position of the particle at exactly the same time, meaning there's no way for us to know exactly where the electron is. For large objects, it's not a big deal. We can do that because they're large, but because electrons are so very, very small, it's next to near impossible for us to do it. And so this became the Heisenberg uncertainty principle. Okay? And this led to a gentleman by the name of Erwin Schrödinger, who came up with what is called the quantum mechanical model of the atom. He put both ideas, de Broglie's and Heisenberg's principle, Heisenberg's uncertainty principle, together, and stated this, okay? So if all particles of matter act like waves, especially electrons, and when electrons were discovered, they have properties of waves, it's impossible to know their location. He came up with the idea of the quantum mechanical model, meaning that we only have generalized probability regions as to where the electrons are located. So if you look at the diagram down in the bottom right-hand corner, you will notice that those little bulbs, those are probability regions done through calculus calculations, which I'm not going to go through, to determine where the electrons probably could be. These are what are considered to be the 90% probability regions as to where the electrons will be located. Now, you're going to say, what does this mean? Well, instead of thinking of Bohr's model as these perfect concentric orbits, we now need to think of the model of the atom as actually this cloud of electrons, where there's not a defined particular orbit that it's going through because these electrons are moving in the pattern of waves. And so you will notice that we have different types of orbitals as showing there in shapes. So we have, for example, a circular one, then you kind of see these weird lobed structures, and then it repeats. It's a large repeating pattern. And that, ladies and gentlemen, leads us to our most important part, which is, well, how do we know where the electrons are? And so scientists wanted to not only have a way of knowing kind of where they are, they wanted to kind of build an address system. And so that's where electron configurations come into play. So if you think about your address, like how do you get to your house? Yeah, you can use GPS, but you have to give someone an address. You got to let them know the city. You got to know the street name. You got to know the street number to know where you are located. And that's exactly what scientists want to be able to do, is to kind of give a generalized location as to where electrons are. And you're going to go, well, why would we want to do that? What's the purpose in this? The whole purpose is to be able to predict how bonding occurs. And so if we know where the electrons are, we can determine what type of bonds could potentially form. So I want you to think of this. In electron configurations, there are basically three main parts. We have what are called the energy levels, okay, which is represented with the letter N, meaning energy level, meaning how far away is the electron from the nucleus. The larger the N value, mean energy level, the further away the electron is. The lower the energy level, the closer the electron is. And when I'm saying further away, I'm talking about from the nucleus. We also need to know what are the sublevels, meaning what do the shapes of the orbitals look like? What do they look like? Are they circular? Are they lobed? Because they all look different, okay, depending upon the sublevels. And then there's only a certain number of electrons that are actually allowed in each one of the sublevels, which are referred to as the orbitals. Okay? So I know this is going to be a little confusing, but let's see if we can work our way through this. All right? So there are exactly 7 energy levels on the periodic table for the elements, meaning there are 7 rings, general ring locations, clouds, you might say, as to where the electrons are located. 7. Why 7? Well, because there are 7 periods in the periodic table. Okay? Now, for each each energy level, there is a sublevel. So for energy level 1, the first sublevel is called S, spherical in shape. For energy level 2, there's 2 sublevels, S and P. For energy level 3, there's S, P, and D. And for energy level 4, there's S, P, D, and F. If we went to energy level 5, it would go S, P, D, F, and then G, and so on and so forth. So it increases each time. So each energy level, there's another sublevel. So each sublevel contains a certain number of orbitals. Now, in an S sublevel, there is 1 orbital. In a P sublevel, there are 3 orbitals. In a D sublevel, there is 5 orbitals. Do you feel a pattern developing? So if we were to possibly predict what the sublevel is for F, what do you think it would be? If you said the number 7, you are correct. Okay? Now you're going to say, it's almost as if there's a pattern. And yes, there is a pattern, ladies and gentlemen. That's what I want to make sure that we understand. The periodic table is a repeating pattern. Look at it. It has a repeating pattern. It will constantly repeat. This is what we refer to as the periodic law. Okay? So again, energy level, for each energy level, there is a sublevel. So if we have energy level 1, there's 1 sublevel. Okay? In each sublevel, there's a certain number of orbitals. For example, sublevel S, there's 1 orbital. For sublevel P, there's 3 orbitals, and so on and so forth. You notice that I just keep going up to F. And you're like, well, where's G? Where's H? Where's the other ones? We'll go into that. Now, each orbital can hold at most 2 electrons. The number of electrons correlates with the number of elements in the block in the periodic table. Now take a look at that little diagram down there in the bottom right-hand corner. Does anyone happen to notice what I've done there with the periodic table? You notice I've got 1s, and I've got 2s, 2p, 3s, 3p, 4s, 3d, 4p. That, ladies and gentlemen, is how we're going to be writing our electron configurations. Now, for orbitals, the one orbital there can hold 2 electrons. 3 orbitals can hold 6 electrons. 5 orbitals can hold 10 electrons. You're like, well, how do you know? Well, what's 1 times 2? 2. What's 3 times 2? 6. What's 5 times 2? 10. Yes, I can do basic math. And this is what you need to be able to do. Now, take a look at the periodic table. Do you see a group area on the periodic table that has a maximum of 2 electrons? Do you see a group on the periodic table that has a max of 6 electrons? And when I talk about this, I'm talking about the sublevels. Look at the S sublevel. Notice that in those 2 groups, the 2s, the 3s, the 4s, the 5s, the 6s, the 7s, 2. When we go to the 2p, the 3p, 4p, 5p, 6p, do you see a pattern developing? Go to D, go to F, count them up. They match the number of electrons. So really the periodic table, ladies and gentlemen, is a cheat sheet on how to write an electron configuration. So let's put it all together here. What is the pattern here? Well, energy level 1, there's 1 sublevel. There's 1 orbital, which can hold a maximum of 2 electrons. In energy level 2, there's 2 sublevels, S and P. The number of orbitals, we have 1 and we have 3. We have 2 and we have 6 for the number of electrons in each one of the orbitals, which makes a total of 8. So let's go back to our periodic table. Take a look. Look at 2s and look at 2p. Count the number of boxes. I count a total of 8. And when you count a total of 8, ladies and gentlemen, does that match what we have for n equals 2 for the energy level? Meaning, do we have a sublevel S and P? And then the S sublevel is always 1 orbital, and in the P sublevel there's always 3 orbitals. And when we add up the number of electrons total, it is 8. So now let's go back and take a look at energy level 3. Now you're going to say, where? Energy level 3. It goes 3s, 3p. But what do you notice down there? There's also a 3d. Add them all up. What does it come out to be? You have a total of 18. 18 electrons. So take a look. S, P, and D. Number of orbitals, 1, 3, and 5. Number of electrons, 2, 6, and 10, which would be a total of 18 electrons. So what we need to do is be able to write the electron configurations, okay, for these elements, all right? You're only responsible for writing the electron configuration for elements 1 through 36, okay? Now, of course, with anything, there are rules. Rules when we write electron configurations. The most important rule, the Aufbau principle, states an electron must be at the lowest energy level first, meaning it must enter energy level number 1 first. The Pauli exclusion principle says that an orbital can describe at most 2 electrons, meaning an orbital can hold only 2 electrons. And Hund's rule says that we must have an electron enter each orbital before we start pairing them up. So you can actually write the electron configurations based upon the periodic table of elements. So let me show you how we can do that. Okay, you're going to go, oh, that's a weird diagram. Well, if you look at the diagram, everyone notice down the very, very bottom, the 1s. How many electrons can you have? If you said 2, you are correct. You can only hold 2 electrons. Now think about that, 2 electrons. The first electron could go into that little box there, and then we would have a second electron that can go in there. Is that now full? Can you put any more electrons? Right, it's full. So the next one you have to go up to is 2s. And then you can go up to 2p. So you have to fill up by energy. But it gets really funky when you start looking at the energy. Look on the left-hand side. You see the 1s. You see the 2s, 2p, 3s, 3p, 4s. And then all of a sudden you got this 3d that shows up in the middle. Numerically, that doesn't make any sense. But if we look at the periodic table, that's how it's arranged. After 4s, you have 3d. Okay? So each electron has a location and it must start at the lowest energy level first. Once the sublevel and the orbital are full, the electron then moves to the next highest energy level. So I'm going to be going through how we write these electron configurations. So if we look right here, okay, if we write the very first element, what's the very first element in the periodic table? Hydrogen, okay, which has how many electrons? One electron. So energy level first has to go to energy level 1. In energy level 1, the sublevel is S. How many electrons are we talking about in hydrogen? 1. So the electron configuration for hydrogen would be 1s1. We write a capital 1 in the front, which represents the energy level. The S is the sublevel, and the 1 that appears to be like an exponent, it's actually a superscript, okay, is representing the number of electrons. So let's look at hydrogen. No, sorry, we just did hydrogen. Helium. How many electrons does helium have? If you said 2, you were correct. So the first electron has to enter the lowest energy level, which is energy level 1. Energy level 1 has a sublevel of S, which has a maximum of 1 orbital, which can hold a maximum of how many electrons? 2. So if we look at that, the helium would be an electron configuration of 1s2. Is it now full? Look at our chart on the right-hand side. Is it full? S sublevel, the number of orbitals is 1. It can only hold a maximum of 2 electrons. It's full. Look at where you are in the periodic table. Take a gander at a periodic table right now. Have it next to you. Helium is all the way over on the right-hand side. And because it's all the way over on the right-hand side, it's now full. So now we have to start a whole new energy level, which would be a whole new period, which would be period number 2. Which means we have to now, if we have another electron, we have to now put that electron in energy level 2. But we build, and we build. Lithium, 3 electrons. It has 3 electrons total. The first 2 electrons have to go in the lowest energy level, which would be 1. Sublevel S, maximum that it can hold is 2. But where's the other electron go? Well, that means it has to go to the next energy level, which is energy level 2. The first sublevel that we see in energy level 2 is S again. It repeats. And then we put it in that 1 electron, so it would be 1s2, 2s1. Go to the next element. Beryllium. 4 electrons. 1s2, 2s, what do you think? 2. Now, take a look at a periodic table. What do you notice? Are we at the end of that column? Now we move all the way over to the right-hand side of the periodic table and we go to the next element, which is boron. We have 1s2, 2s2, 5 electrons altogether. That means it needs to go to 2p1. Now p, take a look at the diagram on the right there. What do you notice about 2p? How many boxes are there? Yeah, each one of those boxes represents an orbital. There are 3 orbitals. And how many electrons can each orbital hold? 2. What's 2 times 3? 6. Count from boron over to neon right now using a periodic table. Look at it. How many boxes do you count? I count 6. Carbon, 1s2, 2s2, 2p, what do you think? 2. Continue on. Next element, nitrogen, 1s2, 2s2, 2p, 3. Oxygen, 1s2, 2p, well, so 1s2, 2s2, 2p, 4. Fluorine, 1s2, 2s2, 2p, 5. And then finally neon, 1s2, 2s2, 2p, 6. We now reached the end of the periodic table. The p sublevel has a total of 3 orbitals, which can hold a maximum total of 6 electrons. Are we now maxed out? Are we at the end of the periodic table? So now if we have another element that comes in with more than 10 electrons, we now need to move to the next energy level, which would be energy level number, you got it, 3, which correlates with the periodic table. That, ladies and gentlemen, is your little cheat sheet. The periodic table is nothing more than a giant cheat sheet when we get right down to it. Okay? Now, here's where it gets fun. If, let's say, for example, we go all the way from 3s to 3p, is that now full? Yeah, and what element would 3p6 end in? That would end up being argon. But if it's full, now we go back to the energy level 4. We now have to increase our energy level. But if you notice, now all of a sudden we have the 3D. And that is because if we go back up here, notice that I told you that 4s has, energy-wise, just a little less than 3D. 3D has a little more energy just because of the number of electrons that are in that sublevel. All right, so let's say, for example, we want to write the electron configuration for calcium, okay? Because this is where it gets a little wonky. But again, I want to point out that I have over there on the right-hand side the periodic table. Now, if you notice my periodic table, it's got the energy levels and the sublevels marked, and that makes it a little easier. So I'm going to start off with my pen here. I'm hoping that this works the way it should. We'll try, technology is fun when it works. So I'm going to write the electron configuration for calcium. Okay, now calcium has how many electrons? Look at your periodic table. Yes, you're going to need a periodic table for this, but if we figure it out, calcium is going to be right about there. So if we want calcium, ladies and gentlemen, it's going to have 20 electrons. No matter what, the first 2 electrons have to go as 1s2. Okay, next 2s2. Then 2p6. If I stop there, ladies and gentlemen, I have written the electron configuration for neon. That's what it looks like. It looks like neon, but calcium doesn't have just 10 electrons. It has a total of 20. So we need to keep going. We've filled up the 2p, so now we move on to 3s, then 3p. So the 3p is full at 3p6. I'm now at the end of the periodic table there on the 3rd period, which would be argon. This appears to look like argon. It's not argon because calcium has 20 protons and 20 electrons. Okay, so if we want to write it for calcium, it would end up being 4s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But what if all of a sudden we want to get to something like iron? Iron has 26 total protons, 26 total electrons. So we need to make sure that we can write that electron configuration. Again, has to start the lowest energy level first, which is 1s, and then 2s, and then 2p6, 3s, 3p6, 4s2. You notice that that looks exactly like calcium. However, there are 6 more electrons we need to place, and that's going to end up in 3d, and that's going to be 3d6. Okay, 3d6. All right. Now, let's say, for example, we want to write for zinc. Zinc is right here. Okay, zinc. It's what the Titanic did. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. 10 is the maximum number for the d sublevel. It has a total of 5 orbitals. 5 times 2 is 10. Now let's say, for example, we want to write the electron configuration for bromine. So bromine, 1s2, 2s2, 2p6, 3s2, 3p, yeah, you called it, 6, 4s2, 3d10, 4p5. Try a couple others. See if you can write them. Check online for your answers.